Hello, this is Papers We Love SF. We are here presenting the paper on towards optimal cardinality estimation of unions and intersections. Papers We Love is an organization where we get together and present papers that we ourselves did not write, but that we learned something from. The recording will be put on YouTube, so if you do not want your questions to be on the recording and your face or voice to be on the recording, please put your questions in chat. Otherwise, feel free to simply unmute and show your face if you wish to view the information. I will now hand over to Kendall, who will be presenting on cardinality estimation. And then when he was done, we will have an open floor for discussions of what we all thought of the paper. Take it away, Ken.
Okay, hi. My name is Kendall Willits. I worked at Samsung Ads for about last 5 or 6 years in ad tech. And I got involved with this problem specifically, which is calculating the fact that it's really hard to get accurate intersections of sets. But a general overview of what we were doing, we had a set of data sketches for ad audiences, typically just aggregated from raw data. And in the beginning of the project, we didn't have a lot of money. We had budget for a few terabytes of Vertica and not really room for the full set of data or the compute that we needed to use that. So we used data sketches, and those would typically we would start with some idea for an audience, like people who had watched a certain program or people that had already seen an ad or had not seen an ad, and feed that into the database and try to estimate the audience size from usually from an intersection or union of a bunch of subsegments or individual days worth of data and things like that. So that worked pretty well. We eventually went to unsampled raw data, really just a big data warehouse of event data that we could query more easily. So, data sketches have pluses and minuses. We got some benefit. We had some pains with these, which I'll probably describe here as well. And then later on, I got into this problem again. We had a hackathon, and I started thinking and reading some papers and kind of dug back into it. And I found this paper, which really kind of coincided with some stuff that I had been thinking about. So I'll get into that next. The main thing is that data sketches themselves are simple. We hash unique IDs into a range of like the unit interval 0 to 1. And we usually take a sampling threshold where we take all the values that are below the threshold and discard all the values that are above that. With a sample like that you're just divide the count of that sample by the sampling rate to get the cardinality. So for individual sketches, it's a simple unbiased estimator. It's about as good as you can get. And there are lots of papers on these, which I won't go over but I did want to get that basic idea that you start with just this little stripe of data and try to extrapolate it to the whole set of data. And that it induces some variance because your sample is never exactly correct or can be above or below the expectation and so forth. So that means sketch intersections are hard. The result can be arbitrarily small, so you can take two really large sets, like the population of the United States and people who watch Game of Thrones or something, and intersect those and get a small number, a relatively small size, and your error in that case.
Was choosing the theta problematic?
Yes. Yeah. So the other part of sketches is that, yeah, you choose a different theta for each set. So for large sets, you tend to choose a smaller theta, and for small sets, you tend to choose a larger theta. And the reason is that in order to get the same relative error, for instance, you need a larger sample on the smaller set, and on a larger set, you often just hit a constant bound on what you really need in terms of the number of samples. So, for instance, a relative error of like 1% would take about 10,000 samples, regardless of set size. And of course, your set is smaller than 10,000, you know tend to take all of it. So there are different sampling strategies and setting the theta at different levels for different sets. And there's what they call a threshold choosing function, which you use to fit whatever criteria you have for accuracy or being happy with what your results you have. So yeah, I'll go into that here, but when you're combining sketch intersections, they have different thetas often. And yeah, there is the fundamental problem that you don't know how small that intersection is going to be, and it could have be dominated by the error and just have no useful results, or have a very bad result, like going into negative, and weird values. So we had a lot of those problems, in the trenches. It definitely happens. So the naive method for doing intersections is to simply take the given two sketches with different sampling rates or different thetas, take the minimum one and discard all the stuff in the other set that's above that, because there's nothing to match it to in the smaller, lower sampled set, and then just base your construct the sketch on the right, which is just it's exactly the intersection sampled at the theta min rate. Again, that has arbitrary variance, and you don't really know what you're going to get from that. And the other thing is you're just throwing away that red stripe there, which I'll get back to. But as sketches have evolved, people have started looking at more and more ways to get a kind of second generation of better estimates. They use a lot of statistical techniques like maximum likelihood, just other seat of the pants methods and inventions, but ways of looking at this and saying, well, what is the overall, what's a better estimator for these? And so this paper is really about that process. Like I wrote my thought process here, which was, we used the naive method for a while, a year or two, and I found work on maximum likelihood estimates and some of the more sophisticated stuff that I mentioned. And as I read through some of these, there was a work from Technion, I think, about intersection maximum likelihood estimates, and they seem to be using the discarded elements, which kind of surprised me, because they don't match anything, and they don't don't contribute to the intersection at all, really, or information about it. But as I thought about it, I realized, well, maybe we can make a correction to some part of the naive estimate that kind of compensates for some things that we find from that extra information. And then I ran into this paper, which someone had already written 2 years before me. So I, didn't think of it. I wasn't the first guy at all, but it was very useful, because it, kind of validated the idea and actually did very detailed variance estimates and much more high level analysis of the problem than I had. I thought the only thing I had was, maybe this is better. So the thing that I thought of, or that this mainly focuses on, is that those discarded elements actually provide well, there are two parts of the intersection calculation. One is determining the fraction of elements that are in the intersection, and then the second is determining the multiplying that fraction times whatever best estimate of cardinality you can find. And so when you have the higher rate of theta 1 here, the higher level of sampled elements, you can estimate the cardinality of this set much better with that, and then multiply it by the percentage in this. I'm sorry, I'm actually behind a slide, but the idea is, yeah, the only thing you can really get out of those extra elements is a better estimate of that set's cardinality than the smaller set, the one that I marked with the exclamation part here. So so the idea is that Daniel's idea, or the main idea was, well, let's get the ratio of elements that's, say, 2/3 here that are in the intersection, and then we'll just multiply it times the best estimate for cardinality, the n hat here, that we can find, which is higher, just using a higher theta value. And this has some it corrects for basically a lot of skew and kind of what I call sampling bias in the process of creating the sketch. As your theta min here, you may have sampled fewer elements than you expected, than the expectation for that range for this set, or a higher number. But comparing it to the larger, more accurate estimate gives you a correction factor that kind of corrects for the density variations or sampling bias, or whatever you want to call it, in that small set that you've calculated the intersection from. And so this is kind of there are a couple. Sorry, let me adjust my window here. Sorry. Wait, I can see it. Okay, sorry. And so the most useful idea in the paper is to for each of these component sets, the input sets, to create this corrected estimate from the whatever extra information you have about cardinality, and then combine them using some kind of weighting. And at the time when I was doing this, I had no idea what weighting to use. And I actually wrote to the author, and he suggested, or pointed out that, it's pretty common just to use a inverse variance weighting or some related technique. So, and the paper has pretty elaborate calculations for the variance of both the cardinality and the ratio, or alpha 1, alpha I ratio that for each set. And I ended up plugging this into Python or something, and coming up with like a page of code of a bunch of these factors and estimates combined into using the product rule for variances and so forth. It was pretty messy, but it did give a much smaller error. And oh, hi, Samson. And then so the net from both just using the basic idea and using the weighting that he gave about a much smaller error on the in the trials that I made. And I and so we mainly, the paper has a bunch of what I generally found also is that the smaller set is usually the one that has the most information that you need about the intersection. It's usually closer because it doesn't have the extra elements. Any larger set just has more extraneous elements that are in the difference but not in the intersection. And so those difference elements create the error in the calculation, and really contribute to a lot of variation, or a lot of variance, or whatever. It's just random noise, essentially. And so one rule of thumb is that you could just we'll weight the smaller set at 1, and use that estimate, and then just essentially discard the larger one. And that's kind of some intuition for what, how this works. What you're trying to get at is to really avoid those extraneous kind of noise. And so now for the paper itself, I wrote this out because the paper has a ton of stuff that I'm not covering, and I'll but I think I'll at least cover some pretty major issues. So one is that I think well, I put it at the bottom here, but he has multiple goals. He's doing a maximum likelihood estimate, but he's also, which turns out to be kind of intractable. You can't find a easy closed expression for calculating it, I think, and they're just generally, it's proof that it exists, but it's not useful. And then this weighted averaging technique where you use this ratio and component estimators, what we call the individual terms that you weight and average, is more practical. But it's a little confusing to switch between the two. And there are a number of issues. For instance, the MLE, it for more than two input sets, when you're intersecting a large number of things, the corrections become kind of exponentially complex in terms of the expression that you're using, I think. There's kind of a combinatorial explosion as you go above and more than two sets. And that's because individual pairs of sets have their own intersection sizes, which could be somewhat larger than the output intersection. And you have to compensate for a covariance related to that when you do this weighting. And so the actual weighting is pretty hard. And so I guess from this paper, I just want, there is a method that exists, and I think he does think that the weighted average will work in general with a kind of covariance matrix calculation that does the weighted averaging for including the pairwise covariance between sets. And but I guess the paper, it's very complete, very thorough, but it has a lot of different results in it that aren't easy to parse. And also another aspect of that is he's addressing a bunch of different sketch types. I covered theta, but it also applies to k-minimum values and to some extent to HLLs and some of the other sets, as well as things like tuple samples and other things. It is useful because you can just do sampling and use this technique and use that. But it's hard to read that because he's naming things that using his own vocabulary or whatever, kind of as a class rather than just saying, this theta sketch or whatever. And also he left out some of the details of the covariance calculation. I and so I'm kind of in the dark on that, and I did feel like it was a little confusing to scale this out to more than two sets. So that sounds pretty bad, but I think there is some hope though, and so yeah, and so the complexity is really kind of if you take two sets that have a large intersection and you form another set that has that just form that intersection and then intersect that with a set that has a small, intersection with everything else, you get kind of a different result than if you go and take two sets, do those things and do those same sets in a different order. And so the complexity is really kind of weighting and combining all those combinations and possibly weighting or discarding some of them or picking the best one or something. And so he hasn't really gotten into that. And it's, well, anyway, it's a good paper I think it'll be a reference for this type of thing. If anybody's doing intersections of any kind of sketches for the next 20 years, they'll probably have to go back to this paper and start with this and work from it and use the results, because some of them are proofs that, MLEs, that they're optimal in many ways, in size or in accuracy, and not size, but in some uh, metrics of how statistical quality. And so he's very thorough about that. And I think you can just look up, is this the optimal thing? Does it have is it unbiased? Is it, is it efficient, or some of these other terms that I don't know very well. But if you're a PhD level statistician, I think you'll really enjoy this paper. So, but again, I think the core technique is not very hard to apply, of applying that correction, of this correction is simple, trivial calculation. You can throw it into your sketch, library or whatever, or add it to on top of the estimate you get, um, to fix your intersection and get some benefit from it. So this part is really accessible. I think that's what's interesting is, he takes a very simple technique and really develops a very complex explanation and proofs about it. But that's part of the problem. It's hard to prove that these work. So last part of the story is this year I took another stab at it, and I made some simplifying assumptions, and I basically started with his paper and tried to, use some of his weightings and things, and found it very difficult, and, used up a lot of pencil lead writing out expressions and things. And I eventually realized I had written out the correction differently from how he had broken basically the same thing, but with a different factorization, if you will, or separation of variables. So I spent some time looking at the right side of this multiplication here in the middle of the screen, where we do some weighting, and I made some assumptions like that instead of just a better estimate of the cardinality, we have the exact estimate. We just don't have to worry about that source of variance. We don't have any variance in it. It's the exact number. And that's actually true in a database context. So if you go into your database and just take a sample of that, but you already know the cardinality, you can, and you add that to your sample, or record that with the sample, you can just avoid that searching for a better sampling rate process and just use the exact number. And that simplifies some of the reasoning about the correction and so forth. And so what I originally or eventually came to realize was that there's kind of I won't get into it here because it's really a different body of work, but there's a kind of least squares estimate of the cardinalities that leads to a weighting that's pretty simple, that gives you I think almost the same effect as what he's describing, with a simpler calculation, and also and again, it does allow you to incorporate the exact cardinalities if you have them. And I did this as part of just a idea of could we build a sampling or sketching system with with these exact numbers and use them in the calculation. And so it turns out you can.
W is the weights. What is the N equation?
So N1 is just the exact cardinality. So Ni or whatever is with a hat on it, it's just the estimate, from whatever sampling rate you have. But again, as I said, if you record in a database context, you often have the cardinality available. So you can, work with that as to measure that sampling bias and so forth, and use that as the correction factor rather than a estimated N. But I purposely made this slide kind of short because I didn't want to get into a whole new step of that. But it is an interesting area, and I think this is a viable area of work. And one thing I found about this technique is that it is more combinable, I think. It's more like well, with least squares, you're generally looking for a closest point to the true value, and so you use some weightings that put you closest to the correct value in whatever space you're in. And so with this, you use just linear combinations to find the weights are just a linear combination that uh, uh, you optimize to get the lowest variance, which is in least squares is pretty easy to figure out. And so yeah, I eventually came up with some stuff that seems to work. I've done the numeric tests and things, and it's generally viable. And I'm not sure if it's really different or if it's the same. It could be a rewrite of some parts of what Ting has written already. But it did at least get, what I chose was to kind of minimize the variance of the individual numerator and denominator and not the overall expression, which is very complex to calculate. And that approach seemed to work and give a understandable result in a kind of Euclidean space. So that's kind of that's most of the talk. I originally got some help from the author himself. He gave some basic stats advice to get me started on this about 2 years ago. And I used his variance estimate instead of trying to figure out myself, like I said. And yeah, it's I think if you are working with sketches or trying to get better accuracy in things, I think this is an interesting direction to go in. I think that there might be some more kind of hacks and things that will work for this as well. I'm not sure if we've really explored all the possibilities yet. Um, but at this point, yeah, that's pretty much all the key of the core of the talk. And are there any questions or ideas of, has anyone used sketches or
I was curious if you could talk a little bit more about, you said in practice you needed to find the intersections of multiple sets that was more than
That's
two.
correct. Yes.
How did you tweak this algorithm in order to get it to do more than two sets?
What I did here was at some point I realized I was just doing a linear combination of vectors. Um, and so I'm still writing this out because I don't have any
Because it
proof
does
or,
seem like you could rewrite both the top and bottom of the
yeah, I
second
did.
term there as
No,
summations.
so the bottom part there, how the line goes across, and I, there's a few. I have a GitHub. I was fortunately this was the last slide I finished just before the talk, so I didn't have time to incorporate it. But on my GitHub, there's an intersection sketch repo that has a write-up of more of the reasoning behind this. And what I really was doing, I realized, was working. If you look at both the numerator and denominator are linear combinations of cardinality estimates, which are just at the time I thought they were linear functors, but they're not. They're just they're functions of vectors, of random vectors of variables. The space I'm working in is where for each element I have a dimension in the space, and it's either 1 or 0 depending on if that element is in the subset. So each vector is a subset and mapped from basically a bitmap of the set. And then if you inner product those and do things, you get intersection size and get norm and variance and things like that from those vector combinations. And I actually worked backwards on this because I kind of had an idea for the weighting, and then I kind of couldn't figure out why it seemed to work. And then I realized it was more like the weighted averaging I was looking at was more like signal averaging, where you take the noise and divide by the magnitude of the noise, which is all variance in the, instead of just some other weird variance. But that turns out to be very analogous to hashing things into, the unit interval and kind of combining those or taking inner products of those um, functions, if you think of that as a bunch of impulse functions or something. Um, I I apologize for not putting more info. Let me just break out of this because I do have more info on that if you would have more questions. I wasn't sure if people would be interested or not, so let me just flip. I've got this, like I said, where is it? Stop asking me.
Right. Does anyone
Oh,
from the audience want to ask a question before we go to sort of more general discussion?
yeah, I could just go to general. I don't have a formal presentation on this, but I could answer questions if you want. Let me see where was it? Sorry, to get the preview.
Hey, Kendall. I just wanted to say hi. It's been a while.
Hey, Samson. Yeah, how are you doing?
Good, good, good.
Yeah, Samson and I worked at Zynga about 10 years ago, so 10 or 15 years ago. So yeah,
Yeah.
we were
I
chatting
imagine
online.
they had some similar data problems.
Yeah, well, we did, but we didn't have any solution. So, this has been my evolution towards knowing something more, all the stuff we needed 10 years ago that, delayed by 5 years that we didn't get to. And uh, the, yeah, so, at the time we didn't even know about hyperlog or anything. We had all these summary things we were trying to do, and we were just adding the numbers and not merging, unique counting uniques or anything, and we just had
So
no
at what
clue.
point do you think it's worth it to just sort of give up and use exact solutions?
Yeah, exactly. Well,
Because one way to do it is to just
I'm
like
kind of that
do it.
way. Like my early, like I was saying earlier, we did actually go to just using exact data, and there's reasons for that. It's just more flexible. But I still like this. They're really interesting problems. They're often very accessible because you can just write a little, like for this, I just wrote a little Python script to test, some intersections and see if the variance went down. So I like them because they're really fun, they're little things you can think about and mess around with without building like a, 500 node cluster or anything.
Did you
But
find union was easier?
union, well, I ended up just using difference from intersection, like n1 plus n2 minus intersection size. And I think it's because in this particular formulation, I had the exact n1 plus n2. And so the variance, like this thing on the right is the union. And the variance is exactly the same as the intersection because I just subtract the intersection from the exact values for the two sets, the independent sets. And so, but the yellow part is the naive estimator where you union things just below theta and use that sample to extrapolate. That has a much wider variance. And that um, but in this repo, I go kind of through like the vector embedding that I use to sort of justify it. And I realized, with weighted averaging, you kind of have, this picture is actually pretty good. So I want to bring this up. But the green part here is the intersection in two sets, like S1 on the left and S2 in the middle here. And then the blue and gold part are the difference components, which this is a God's eye view where you can look into these things and say, oh, that's the magnitude of each. And these are hashed and put into a histogram. So you can kind of see where the variation comes from. If you just took one vertical slice of this and extrapolated, you get, widely varying estimates. And so that's, you could think of theta, the naive estimator, is just taking from 0 to some number here and then extrapolating from the kind of jaggy histogram that you see there. And what I found though is if you average these, the weights that work are actually the ones that equalize the blue and gold area the difference size. So you divide by the difference size, and which is actually an approximation because you're taking n minus the estimated intersection size, and then you divide by your weights go into that, and it's like a second order thing or a second level correction where you correct for the kind of noise magnitude. So this is exactly the same weighting as signal averaging. If this were a signal and the blue and gold were the noise, in a time-based signal or something, you would do exactly this weighting and get a minimal signal to noise ratio, which is also kind of minimal variance. And so this was what I came to after fiddling around with a bunch of formulations and things, and realized that the problem was really that the excess noise part, not the base part of the intersection, which you can essentially ignore as far as weighting is concerned. And so I went into Python and actually created this so I could look at this idea and do it. But yeah, but this is actually a linear thing. And so like when you scale out to n different things, you actually just take like n different weights, and you have like a what's actually a convex hull. I had to look it up, but it's a combination of vectors, some of which may be linearly dependent. They're not independent, which is easier. So in the two set case, they are linearly independent, like the blue and gold vectors, if you want to call them, think of those as summed into the base vector. Those components are orthogonal. And so you don't have to, somewhere in here I've got your least squares, proximity is just like a triangle, like a right triangle, and you find the altitude, which is let me see if I can have it up. Sorry if I got a flip displays, but you can also do it by kind of taking the inner product and doing some basic least squares where you find where the derivative is 0 and get the minimum from that. It gives the same result because it's just it's a linear thing. It's really easy to calculate. But for n different vectors, you have this convex hull problem where you're trying to find the combination of these things that is closest to essentially the green vector out of a big number of combination, or a large simplex or convex hull of space of combinations, and n-dimensional space of weights. And so that is kind of a linear optimization problem, I think, or it's at least somewhat of a calculation to get that the best variance. Sometimes I think you can approximate it. I looked up an algorithm, and the best they could do was kind of approximating the closest combination. But this formulation at least gave me a geometrical intuition for what I'm trying to do, is trying to get the like I said, these noise vectors combined in a way that minimizes the noise and maximizes the green component, the intersection relative to them. And so that's kind of what there's more stuff in there, but I'm still writing out this, like it just kind of ends without any conclusions or anything, but I may be quite similar to what he's proposing. I think there's some similarities, and I'm trying to understand whether he proposes a method based on basically inverting the covariance matrix and getting weights from that. I'm gonna try to write that out and see if I can, get if it's equivalent or similar or something different. But this is actually just way easier. I mean, it's just or at least in the two set case, it's a pretty simple expression.
To a first order, it should be similar.
Yeah. And I think, well, as I thought about it, like I said, I don't think he gives a weighted, a weighted combination exists for the independent estimators that he has. They're all broken, they're all these, he has basically two or n different component estimators, which are quite complex. They have, the two different estimates of cardinality and the ratios and things. And I just said, well, maybe I'll just try to, minimize estimate the small piece of this, or take out some of the, like I said, factor it out a little bit. Focus on one of the factors having minimal, lower variance, and it ended up with just looking at this. It gave me some intuition to realize that the uh, the variance in the that you get from something like just a linear combination of cardinalities or cardinality estimates is pretty much a function of this kind of vector space that you're working in. And I'm kind of a stats caveman, so I don't really know if this is how stats, apparently they used something like this for signal averaging and some certain formalisms like this, but I'm honestly kind of lost. I'm not a
Yeah, that was one of the things that surprised me is, so the closest thing to this that I've ever used was looking for unions, not intersections, but it was
yeah,
every server is keeping track of a hash of the user ID of every user that touches that server. And
right,
then you ask questions like, okay, what is the monthly active users
right.
across
What's the
all
union of
servers?
all that?
So what we were collecting was essentially the min 50 hashes for every server for every hour.
Right.
And then when you wanted to
So,
know what was your cardinality estimate for the
right.
entire month, you just took the min 50 of all of the sets. So you could just have a
Yeah.
really cheap aggregation function that was just rolling through everything, keeping the min 50 for every server for every
Yeah.
time
If
slot.
you are, I would recommend this technique for that,
Uh,
or actually
and
from
then didn't do
or
statistics until after. This seems to do the statistics on the size, on the cardinalities, rather than just taking the mins of everything and then doing the statistics at the end. And I wonder if this is going to be more accurate than what we did.
I think it would be because, yeah, this is exactly the case that he's addressing. And again, he's got a couple ideas in there also with KMV or whatever, like 50 minimum values or whatever, that some of them are just common sense, like for union, you do you can do it differently. You don't have to resample at the minimum or something. I can't remember exactly. I've got to look. It's in there, but he's very good at finding these little optimizations and then going on for 10 pages about the variance or something. But yeah, I would look into something like this because yeah, in this case I have, like I said, I start with the exact cardinalities, so it's more of the database case where you know upfront before you do the sketch or sample what the total cardinality is, and you're only interested in maybe intersection cardinalities where you can't determine that a priori. Um, so you with that information, this technique works pretty well, and that's why I was saying use the input cardinalities to improve things. And that's kind of what, the fundamental question is, can these combine into the output and give something in the output that also is closer to the true cardinality? So the answer is yes, it seems to work. But in your case, if you just have estimates, there are different, I think in your case, if you had 50 minimum values, I think you said, you would go through and find out with Canvas, you have you kind of figure out what the maximum of those is, and that's your threshold, and then it varies from set to set, automatically, just because some sets are bigger and the 50 minimum are smaller, or vice versa.
Right.
So
Clearly, we were throwing out a
use
lot of
that
data.
extra
If you have,
information about cardinality. Yeah. So like for instance,
right,
if
if
you
you have
run,
50 from
yeah,
every server from every
yeah.
hour, and you have however many hours there are in a month times 1,000 servers, and then you only use 50 of those data points, like you've thrown out almost
Yeah,
all the data.
I would, I I'm not sure if, yeah, his technique would definitely, he does say it will work. It's tractable to do the matrix, the covariance matrix. And I think the covariance, like the off diagonal terms, are actually something like the pairwise intersection of those sets, you know, and so, but anyways, you can get that, do some matrix stuff, get a weighting and get a better, tighter, estimate of your 50 way or, you know, 1,000 way union. And that's definitely what he's saying here, and it's definitely applicable here. And I haven't heard of anybody really doing it. I guess I just have a lot of open questions, like, can I do it, you know, 1,000 way, you know, 1,000 way by 1,000 square matrix and get the weightings and you know, is that even doable in this you know, type matrix or whatever. And in my case, I think I did get I'm getting more insight into, you know, what the, like I said,
Still
what the
probably cheaper than
contributors
using.
are to the problem. You know, it's like this, every set gets hatched differently, and individual elements fall into different buckets, and the cumulative effect, you know, is kind of a skew on the estimate that you have to correct for. So but yeah, I think it's you know, it's definitely worth doing. And so yeah, if there are any other, I'm curious if we could find you know, a problem to try this on, or somewhere where we, you know, want to do the work to apply this fully.
If there are any more questions that are relevant for the YouTube recording, then I'll invite people to ask them now. Otherwise, I will stop it so we can go to the more casual social time asking questions.
Yeah, thanks everyone.
All right, let's thank our speaker.
All right, thanks for showing up. I realize that we also have YouTube folks, and welcome to those later on that might view this. But yeah, yeah, I'm glad we got together today.
Right. And as a reminder to all the people on YouTube, show up for the live session and you'll get to stay afterward for the more social time. And we have open speaker slots. So go to the meetup page and post and reach out, because we would like to have you come here and share a paper that you love with us. Thank you very much.